Okay, this is project test number 8, video number 4, and we're going to be covering problems 31 to 40. This will be the last video for project test 8. The director of a marketing department wants to estimate the proportion of people who purchase a certain product online. The director originally planned to obtain a random sample of 2,500 who purchased the product. However, because of budget concerns, the sample size will be reduced to 1,500. Which of the following describes the effect of reducing the number of people in the sample? So we're reducing the sample from 25 to 15, 2,500 to 1,500. What's going to happen? Well, as the sample decreases, variability goes up, right? As n goes down, variability goes up, and the opposite is also true. So the variance of the sample will increase. Definitely looking for increase. The variance of the population. By the way, the population will never change. It doesn't have an impact, right? We can't change that. The variance of the sampling distribution will increase. Ooh, that's interesting. The variance of the sampling distribution will decrease. No, can't decrease. The variance of the sampling distribution will remain the same. No, there's going to be a change. So now we have a question. We have two of these that have increased. Which one is it? Changing the sample size does not change the variance of the sample. Changing the sample size changes our estimator. In other words, we will be off by more if we decrease it. This is my best choice. All right. Be really careful of that. They were setting you up. Again, this was one of the questions where they were setting you up for something, because it's like, hey, I know that my variation increases. The first thing was increase, but the sample variation is not what's changing. It's our estimator. All right. So the estimator, the variance of the estimator will increase. All right, number 32. Slide this all the way down. From a random sample of 1,005 adults in the United States, it was found that 32% own an e-reader. Which of the following is the appropriate 90% confidence interval to estimate the proportion of all people in the US who owns an e-reader? So our confidence interval has this formula: p hat plus or minus z star p hat q hat over n. So p hat 0.32 plus or minus 0.32, and then 1 minus 0.32 is 0.68 over 1,005. So real quickly, we can get rid of this first one, that one right there. We can also get rid of this one right here, because it's not under the radical. All right, the others, we need to calculate z star. So let's go ahead and calculate z star. Second vars, inverse norm, parenthesis 1 minus, and we are wanting to calculate a 90% confidence interval, 0.90 divided by 2, mean is 0, standard deviation of 1, and we end up getting 1.645. So we need to find the one that has a 1.645, and that happens to be E. So the answer to 32 is E. Number 33, measuring the height of a tree is usually more difficult than measuring the diameter of a tree. Therefore, many researchers use regression models to predict the height of a tree from its diameter at 4 feet 6 inches from the ground. The following computer output shows the results of a linear regression based on the height in feet and diameter of recorded from 31 felled trees. And so basically what we're saying is height equals something, all right? Which of the following is the 95% confidence interval for the slope of the population regression line? So please remember, this is the y-intercept. A lot of times they just call that a constant. They don't even call it a y-intercept. They don't even put the word intercept. They just say constant. So anytime you have a word that's a descriptor, that's going to be your slope line. So this is my slope line. So this is what I need to pay attention to. So we're looking for b hat plus or minus t star times the standard error. All right, well, they give us b hat is going to be 1.054 plus or minus. We'll come back to t star in a moment. We have a standard error of 0.322. We don't have to do anything with that. Now, this is a regression, so we have to be really careful. Our degrees of freedom are going to be n minus 2 because it's a regression. So degrees of freedom in this case are a sample size of 31 trees, 31 minus 2. So our degrees of freedom are 29. So they want to do a 95% confidence interval. So let's calculate our t star. Second vars, inverse t, parenthesis 1 minus 0.95, close parenthesis, divided by 2, degrees of freedom are 29. And we end up getting 2.045. So we're going to end up with 1.054 minus 2.045 times 0.322. That'll be our lower bound. And our upper bound is going to be 1.054 plus 2.045 times 0.322. And that's our upper bound. So let's calculate those using our calculator. 1.054 minus 2.045 times 0.322 equals a lower bound of 0.3955. And we're going to calculate the upper bound, 1.054 times, plus 2.045 times 0.322. We get an upper bound of 1.712. So my answer choices are 0.3955. That looks pretty good for the lower. 1.712 for the upper. 33 is B. All right. Moving on to 34. A group of 80 people who had been diagnosed as pre-diabetic because of high blood glucose levels volunteered to participate in a study designed to investigate the use of cinnamon to reduce blood glucose to a normal level. Of the 80 people, 40 were assigned to take a cinnamon tablet, and the other 40 assigned to take a placebo. The people did not know which one, so we have placebo, we have cinnamon, and we have placebo. We have 40 here and 40 there. All right. The people did not know which tablet they were taking. Their blood glucose levels were measured at the end of 1 month. The results showed that 14 people in the cinnamon group and 10 people in the placebo group had normal blood glucose levels. For people similar to those in the study, and by the way, they just qualified it, for people similar to those in the study, in other words, if you're similar to who the 80 we tested, do the data provide convincing evidence that the proportion who would be classified as normal after 1 month of taking cinnamon is greater than a proportion who would be classified as normal after 1 month of not taking cinnamon. So here's our null hypothesis. P cinnamon equals proportion placebo, where that is the proportion of people who had a drop. Now, proportion cinnamon is greater than this because we want to know if this is going to be greater. Well, our equation for this problem is the Z equation, and it's P hat 1 minus, or P hat cinnamon minus P hat, and it doesn't matter which way we go. Now we need to be very careful here. This is going to be P combined, Q combined, over N1 plus P combined, Q combined over N2. And remember, P combined equals X1 plus X2 over N1 plus N2. And we would need to plug into all of these if we were actually running a hypothesis test. And I'll go ahead and if we were actually running an FRQ. So in this case, we had 14 plus 10, 40 plus 40. So this is 24 out of 80. And so our combined is going to be 0.30. So what this is going to look like is 14 divided by 40 is 0.35. And this is 10 divided by 40 is 0.25. So if I were filling in my work, I would go 0.35 minus 0.25. We already said P combined was 0.3. This is 0.7. This is 40 plus 0.3 times 0.7. And they both happen to have the same sample size. Now that would be showing my work, and then I'd go to the calculator. Obviously, since this is a multiple choice problem, we can go straight to the calculator. We have two proportion z-test, and we have 14 out of 40. Then we have 10 out of 40. And we said we needed a greater than and we calculate, and we get a pretty large p-value. We get a p-value equal to 0.164. If we take a standard alpha of 0.0500, this is greater, so we're going to fail to reject. And let's look at our answer choices. The question was, is greater than, for people similar to those in the study, do the data provide convincing evidence? So we're looking for convincing evidence, and the answer is no. Conclusion can be made about cinnamon because the people in the study were volunteers. No, we don't care that they were volunteers. Volunteers are usually used for experiments, but because they were volunteers, we said that they had to be for similar to those in the study, so that's not it. There is convincing evidence at 0.01. No, our p-value was 0.164, which is greater than 0.01. So there's not convincing evidence at that level. Moving on, there's convincing levels at 0.05, and it's like, no, our 0.164 is greater than a 0.05, so not convincing. There is convincing evidence at 0.1, and it's like, no, 0.164 is greater than 0.10, so not convincing. There is not convincing statistical evidence at any reasonable significance level. That's correct. We'd have to get a very large alpha level. Alpha level 0.2 have been convincing, but we don't do that. About 0.10 is about the largest we ever use. Okay, number 35. A student worked on a physics project investigating the relationship between the speed and the height of roller coasters. The student collected data on the maximum speed in miles per hour and the maximum height in feet for a random sample of 21 roller coasters with the intent of testing the slope of the linear relationship between maximum speed and maximum height. However, based on the residual plot shown, the conditions for such a test might not be met. So basically, we should have 21 different dots here showing the different roller coasters, and we have height. Remember, residuals should be centered on 0, and we should show no pattern. But what I notice here is right here, I'm pretty close to the line, but as I move farther this way, I'm getting farther and farther away. All right, so we don't talk about errors being independent. The sum of the residuals is 0. It better always be 0. So that's always the case. The expected value of the errors is 0. No, the sum of the errors is 0. There's a linear relationship. That's not what we show here. We show that on a scatter plot. We don't show that on the residual plot. So this is shown on a scatter plot. The variance of the response variable is constant for all values of the explanatory variable. And the variance would be the spread of the data. Well, here I'm pretty close. So I have a fairly small variance and it gets gradually starts to get bigger. So the variance does not appear constant. And because the variance does not appear constant, it appears we're violating this condition. A researcher conducted a t-test of the hypothesis mu equals 38 versus mu equals 30, mu does not equal 38. So we have a 2-sample test. And here's our claim at 38. And we have a not equal test. The sample mean was 35. So we actually, this is the population mean, and we actually ended up with an X bar right here of 35. And notice at 35 is less than 38, so it's there. And we ended up with a p-value of 0.0627. Now, because this is a two-tailed test, my p-value is actually divided into two tails. So 0.0627 divided by 2. So that means I have 0.03135 in this tail, and I also have 0.03135 in that tail. What would the p-value have been if the researcher had used an m less than 38? Oh, less than, that's this direction. Had they used the less than, it would have been 0.03135. Well, how did I get that? I multiplied by 1/2. So this is E. But let's check this out. What if they had done a greater than, HA for mu greater than 38, and they still had an X bar equal to 35? Had they done that, we still would have had our mean of 38. We still have 0.03, well, excuse me, we still have a 35 here. This is my X bar. Well, at this point, we know that we have 0.03135 in this tail, but if we had a greater than, had this been a greater than, we were looking at this area, it would have been 1 minus the 0.03135. So it really depends on the direction. It depends on the X bar and the direction of the test. If it had been less, since it was less than, it was just a 0.03135. Had it been a greater than, and we had an X bar down here, it would have been 1 minus that. But in this case, 36 is E. All right, number 37. Trying to trick you again. High school students from track teams in the state participated in a training program to improve running times. Before the training, the mean running time for students to run a mile was 402 seconds with a standard deviation of 40 seconds. After completing the program, the mean running time for students to run a mile was 368 seconds, which with a standard deviation of 30. Let X represent the running time of a randomly selected student. We have a randomly selected student before training, and then let Y represent the running time for the same student after training. Which of the following is true about the distribution of X minus Y? Okay, so basically we're just going, okay, what are we expecting? We're expecting it to go 402 minus the 368. All right. However, Well, first off, we measured them before and after. So obviously we're working with a mean difference. We're testing someone twice. If I test someone twice, the scores are not independent because they're dependent on the individual. Because they're independent, I cannot combine standard deviations. All right, so the variables X and Y are independent. No, they're not. There's the same person. It depends on that person. The variables X and Y are independent. Once again, no, they're not. It depends on that person. The variable X and Y are not independent. Therefore, the standard deviation is 50. No, we can't calculate the standard deviation because to calculate standard deviations, the variables must be independent. The variables X and Y are not independent. Therefore, the mean is 34. Let's check that out. 402 minus 368, and we can calculate the mean, and it is in fact 34. And the standard deviation cannot be determined. That's true. The variables X and Y are not independent, therefore neither the mean. No, that's not true. You can still calculate the measure of the mean. Now, real quickly, had they been independent, my standard deviation would have been this: 40 minus 30, because it was an X minus Y. But we know we can't, we know we have to add them and square them and take the root of them. And if we did that, we would have gotten a standard deviation of 50. Real quickly, 40 squared plus 30 squared, oops. 40 squared plus 30 squared, and I'm taking the square root of that, and I get 50. Now, I can only do this if they're independent, but in this case, they're not, because the same person was tested twice. It depends on that person. How that much they improved depended on the actual individual. All right, number 38. A polling organization surveyed 2002 selected adults who are not scientists. So NS is 2002. And 3,748 selected adults who are scientists. Each adult was asked the question, do you think that genetically modified foods are safe to eat? Of those who are not scientists, 37% responded yes. So the p-hat for not science is 0.37. And those who are scientists who said yes, the p-hat for scientists equals 0.88. Which of the following is the standard error used to construct a confidence interval for the difference between the proportions? Well, remember, the confidence interval formula is going to be something like p-hat not science minus p-hat science plus or minus z star p-hat not science q-hat not science over n1 plus p-hat science q-hat science over n2. All right, so in this case, we have 0.37. 1 minus 0.37 is 0.63 over 2002 plus 0.88 times 0.12 over the 3,748. All right. So for this one, we need to make sure everything's under the radical. That's not happening. That's split up, and we can't be subtracting. So number 38 is A. Number 39, a polling agency conducted a survey about social media in which each person in a random sample of 1,000 men and 1,000 women were asked what factor he or she considers to be most important when deciding whether to connect on social media with another person. The responses are shown in the table. And if I added these up, and by the way, you should always total these. If I totaled these up, This will total to 1,000. I'm just going to tell you real quickly it does. This also totals to 1,000. This is 86. This is 60. This is 170. This is 434. And this is 1,250. What is the contribution of the chi-square statistic for men? So we're looking for men. Who selected business networking as the most important factor? All right. So first off, chi-squared. We're looking for the contribution, which means we're looking for this, we're looking for the observed minus the expected squared over the expected. Well, that means I need to calculate my expected. All right. So I need to calculate my expected. Well, the expected value, hold on for just a moment. I apologize for that interruption. Okay, so I didn't finish totaling this up, so I need to finish totaling this up. The total of the entire table was 2,000. So I need to calculate my expected value. Well, expected value equals n times p. So I need to find out the probability of this. Well, basically, in this case, my probability is the probability of the intersection. I want the probability of the intersection, which is the probability of A times the probability of B equals the probability of A and B. That gives me my expected value or my probability. So this is going to be 60 over 2,000 times 1,000 over 2,000. And that gives me the probability of my intersection. When I multiply this out, 60 divided by 2,000 times 1,000 divided by 2,000 equals 0.015. But that's the probability. Well, what was my sample size? Because now I need my n. My n was 2,000. So I'm just going to multiply that by 2,000. And I find out that my expected value equals 30. And I'm going to show you another way on the calculator to do this, but this is what you're doing. This marginal probability times this marginal probability gives us the joint probability of 0.015. You take the joint probability and multiply it by the total sample, which was 2,000. Now, I know that my expected is 30, so minus 30. And in this case, my observed was 45. So here we go. 45 minus 30. I'm going to go ahead and square that. And I'm going to divide by 30. And I end up getting 7.5. So 39 is C. Now here's another way to go ahead and do the same work. Because I know that I'm looking for to see whether or not these are independent, to see whether or not there's an association, I will go ahead and go second matrix, edit, press enter, and I have 2 rows and 1, 2, 3, 4, 5 columns. So I need a 2x5 matrix. So 2, enter, 5, enter. And then I enter the data into the matrix. All right, I do not need to include the totals. All right, so I've done that. Now, once I've done that, I just clear the screen. I'm gonna go ahead and run a chi-square test for independence, or just a chi-square test. Press enter and calculate. And it calculates everything for me. Now I'm gonna go back to second matrix, press edit, and I'm gonna drop down to B because that's gonna be my expected value matrix. And I need to count over 1, 2, 3, 4 columns. 1, 2, 3. There's my fourth column right there. And there's my observed value, or excuse me, my expected value of 30. Right? So that's another way to get your expected value. Next thing, number 40. A national survey asked 1,501 randomly selected employed adults how many hours they work per week. Based on the collected data, a 95% confidence interval for the mean number of hours worked per week for all employees was given. Which of the following statements is a correct interpretation of the interval? They're not asking for the confidence level, they're asking for an interval, the interpretation of the confidence level. So we are 95% confident the true population mean amount of hours worked per week lies within the interval. So 95% of all employees work between this. No, we didn't say that. We're just 95% confident we have the mean. The probability, we don't like saying that. Just get rid of it. Of all samples of size 1,501 taken from the population, 95% of the samples will have a mean. Wait a second. No, we don't make comments about the sample. We make comments about the population. We know the sample. We know the sample. We are estimating the population. We are 95% confident that the mean number of hours worked per day for employed adults in the sample, oops, there's that bad phrase. Matter of fact, we know the X bar is in the middle of this sample, and whatever that X bar is the mean amount for the sample. And it'll always be in the middle of the confidence interval. We're making an estimate, not about the sample, but about the population. We are 95% confident that the mean number of hours worked per week for all employed adults is between 41.18 and 42.63. And notice we said for all. When we say for all, that's another word for population. Okay. All right. Thank you. And that closes out that video.